Hello, my name is Travel Edna Takaisa. I'm from Group MLSW24, and today I'm presenting the project under the title Real-Time Biomechanical Skill Classification for Bike Dispatch via Cloud Deployed Long Short-Term Memory Neural Networks. This is the overview of everything we're going to cover today: an introduction, problem statement, research questions and objectives, research contributions, the methodology, dataset description, results, model selection and deployment, conclusions, anticipated limitations, as well as the acknowledgement. Well, road accidents involving bike riders, especially in Uganda, has become so rampant and has become a safety concern, especially due to the lack of fundamental skills by our riders. For example, safely moving from one lane to another or simply navigating along a corner. And so our system presents a solution where riders are able to demonstrate their competence before they are able to get the bicycles to ride at dispatch points. Basically, the demonstration is recorded and evaluated, and the verdict is given based off poor, good, or average. And then the rider is able to go on the road having been assessed. For the domain application problem, basically our smart rider assessment system is designed to assess the skill level of a particular rider based off a short video clip, whereby the system focuses on analyzing the behavior or riding behavior using video data to evaluate rider skill and detect unsafe rider patterns, which may not be seen by a naked eye or by a person just judging using their naked eye, but rather using a system. For our computational problem, it basically involves automatically analyzing video data to extract biomechanical features, which we extracted 7, which are balance, posture, confidence, upper body stability, pedal rhythm, pedal consistency, as well as the speed consistency. Then using these 7 features, we're able to use machine learning techniques to identify patterns in rider movement that distinguish the skilled from unskilled riders. So our system is able to process video frames and extract motion features, and then apply learning algorithms to group riders based on the similarity in riding behavior. For our research question, can unsupervised machine learning reliably differentiate skilled from unskilled riders using only visual biomechanical features? For our objectives, we're able to conduct comprehensive exploratory data analysis, as well as to assess the rider skill level using the rider film. For our research contributions and outputs, we got a rider skill dataset, 2 in this case, which is the overflow dataset, as well as the ACF10 dataset. We produced a comprehensive visualization exploratory data analysis suite that systematically validates the cluster quality. We built 8 models, 4 models for each of the datasets, and we chose our best, which is the long short-term memory neural networks, which we deployed. For our methodology, we started with the problem definition, which is the lack of fundamental skills, lack of a way of assessing the skills of riders, and as a result, we have accidents happening due to the lack of skills of our riders. We obtained data sets, 2 in this case, performed an EDA, trained our 8 models, deployed our base model, applied 2 compression techniques, knowledge distillation as well as pruning, and deployed the best compressed model. For our dataset description, we have 2 datasets, which is the ACF101 dataset for human action recognition, whereby we mainly focus on the biking class, which contains videos of our bike riders, which are then used to determine the behavior patterns that make the riders to make mistakes, as well as a buffer dataset, which shows still images of our cyclists in varied environments. And in this dataset, we'll be looking for balance, whereby we shall be measuring the hip alignment of our given rider, posture, which basically looks at how the torso is aligned with the hip. Confidence is just measures the measures to check if the post detection algorithm can clearly see the rider within the front. Speed consistency basically looks at the consistency of the limbs during the riding process, which are the legs, the hands, as well as the knees. For the upper body stability, we are looking at the positioning of the shoulders. Pedaling rhythm, we are looking at how consistent the pedaling is over time. And lastly, pedaling symmetry, we are looking at if the legs are moving evenly during the riding process. For our EDA visualizations, we have the cluster distribution, which is looking at the number of samples which have been classified as skilled as well as unskilled. This is after the media purpose extraction has happened, which means some of our very unclear frames as well as images were dropped during the extraction, and the clear ones that remained are the ones that we used to perform the EDA. As you can clearly see, we have a higher number of skilled as compared to the unskilled in the upper visualizations. In the lower visualizations, we are seeing data set source contribution, seeing how many samples are within each data set before being classified as skilled or unskilled, still after the media purpose extraction. And then we are able to split these per cluster in each of the data sets to see the skilled versus unskilled in both the RoboFlow data set separately from the UCF101 data set. For the split distribution by source, we are looking at how our samples are, how many samples we have within the different splits we have in the individual data sets after the media purpose extraction. As you can clearly see, we have 3 splits in the RoboFlow data set and 1 split in the UCF101 data set, which has also been demonstrated in our lower visualization. And then the cluster split by UCF class is done to distinguish between the skilled versus unskilled in the UCF101 dataset. For the media purpose detection rate by source, first we're looking at the detection rate by source, whereby we see that we clearly have a lower detection rate because basically our media purpose was removing any unclear videos as well as images and maintaining only the easy and clear images as well as frames to be moving on and to check from those. So our detection rate was relatively a bit low, and then that explains why our input samples are relatively higher than the detected samples within our data sets. The cluster balance per split, we are looking at how balanced our clusters are among the splits, and as you can clearly see, we still have a clear balance within the skilled as well as the unskilled splits within the data sets. As you can clearly see, we have a 71%, 74%, 73% for the skilled across the splits, and a relatively balanced unskilled samples within the 3 splits. Moving on to the correlations, we are seeing how our 7 features are closely correlated with each other, and our highest correlation is 0.88, which is between the posture as well as the upper body stability, meaning that for a person to have a good posture, the upper body stability must also be very good. Moving on, in these visualizations, we are just seeing which of the features are able to clearly distinguish among the 3 classes we have, which is the poor, average, as well as good. And as you can clearly see, we have a very good score for upper body stability as well as posture, meaning these ones clearly identify and distinguish among the 3 classes. And then we have relatively a bit low scores for balance, pedal rhythm, as well as pedal symmetry, but these are as well are able to distinguish among the 3 classes. Confidence and speed consistency, on the other hand, may not be very good at distinguishing between the 3 classes that we have. The cluster distribution of the sequences extracted from the frames has been demonstrated in this visualization, and we have poor and average at 33% both, and then for the good we have it at 34%, and this is for the UCF101 dataset. For the mean feature score by class, we're basically looking at how each feature performs under each class, and as you can clearly see, relatively have a higher number of good. The score for good is relatively high across all except the speed consistency, and also average is relatively high, which means that most of our features are able to clearly distinguish among the classes. For the feature box plots by class, we are able to mainly concentrate on the posture as well as upper body stability, as these ones are able to also clearly distinguish among the 3 classes we have. poor, good, as well as average, as compared to all the other features that we have here. This has also been demonstrated in the feature distributions by class, as you can see the posture and upper body stability, very well distinguished among the classes that we have. Moving on to our models. First, we are going to talk about the K-means. The first four models were trained on the RoboFlow dataset, which is the dataset containing the still images of the cyclists in the varied environments. For our K-means, it basically partitions biomechanical features into distinct skill tiers. And for this case, it takes the 7 biomechanical scores per rider and then initializes our K as equals to 3 centroids and assigns every rider to the nearest centroid. It recalculates the centroid as mean of assigned points and then repeats this until the centroids stop changing. The 3 resulting clusters are then ranked by the composite score, evaluated by the matrix, and then mapped onto poor, average, or good verdict. Our second model is the DB-scan, which basically identifies clusters as regions of high density and assigns regions of low density as noise. So it basically takes 7 feature matrix for every rider and looks within a radius called the epsilon to find neighbors. And if a point has enough neighbors, it then becomes a core point and starts a cluster. The points near that core point are then pulled into that cluster, and any rider too far away from that cluster gets labeled as noise, meaning that the model refuses to force classify these ones. And so the remaining core point clusters are then ranked by a composite score evaluated by a matrix and mapped to whether poor, average, or good verdict. Moving on, our third model, which is the agglomerative clustering. This one basically just starts by treating every rider as their own cluster, leading to very many different clusters. And then it repeatedly merges the 2 closest clusters using the word linkage, which minimizes the variance within each merged group. This then builds upwards until we cut the dendrogram at k is equals to 3, leaving 3 groups ranked by the composite score evaluated by the matrix, and then mapped onto the poor, average, or good verdict. Then we move on to the Gaussian mixture model, whereby this one just initializes 3 Gaussian components. It alternates between computing how likely each component generated by each rider's data in the E step and updating the component shapes in the M step, and it repeats this until convergence. It flags any rider below the 70% confidence level as the borderline, then maps the remaining soft assignments to the poor, average, or good verdict. These next 4 models are from the ECF1 dataset containing the video frames, and we start with the standard vector machine, whereby this one basically works well with the small datasets, and it just basically takes 6 frames, each with 7 biomechanical scores, and flattens them into 112 values. It normalizes them with a standard scalar. Then the RBF kernel maps those 112 values into a higher dimensional space where the 3 classes become linearly separable. The model then draws boundary that maximizes between the poor, average, and good, giving a verdict. Moving on to the graphical neural networks, which is our GNN, we basically operate with connected nodes, whereby we treat the rider's body as a graph with 33 joints as nodes, and then the bones as edges. And across these 16 frames, we're able to add temporal edges connecting each joint to itself in the next frame. The 3 attention layers then let the joints communicate and build full body understanding before pooling summarizes them into a single verdict of whether it is poor, good, or average. Next, you're going to look at the standard convolutional neural networks, which is the 3D CNN, whereby this one basically learns patterns that exist across multiple frames at once. This one basically processes all the 16 frames at once as a volume. Then each convolutional layer learns increasingly complex motion patterns from basic edges to full cycling coordination. Then the global pooling summarizes the movement patterns into one vector, and the dense layer outputs the verdict as good, average, or poor. Our last model was the long short-term memory neural network model, which was our best model and the one we deployed, which is basically a neural network specifically built to understand sequences or data that changes and develops over time. It was chosen because it understands time by reading 16 forms sequentially and detecting trends like deteriorating balance or improving rhythm than the SVM can. Then it scales better because prediction time stays fixed as the training data grows. It's very architecturally correct for the task because it was designed for sequential motion data, which is what cycling analysis really requires. This is the architecture of our model, from the input to the LSTM first model, then to the dropout, then the second LSTM, then the second dropout, the dense layer, and then lastly, our output. Our LSTM basically reads 16 frames sequentially, one at a time, maintaining the memory of what it saw before. Then 128 unit layer captures the full motion pattern, and the dropout layer then just prevents overfitting. The 64 unit layer then compresses it into summary, and the dense layer then outputs the three possibilities, which is good, average, or poor, which is our verdict that we need for a given rider. So our text accuracy for this was 98.60%, and this was quite high and good for us. Moving on to the deploy pipeline and system architecture, we have basically four layers here. First, the development layer where we did our coding. The files were written and edited in our local machine, and since they were too big to be stored on Git, we stored them on the Git LFS. Following the build layer, whereby this is where we have our Docker file that defines the environment. Then the cloud layer, whereby we have two working spaces here, the API space which runs the Docker file, and then the UI space, which is basically a simple static file running on the browser, such that when a video is uploaded, it just sends it to the API space and shows the feedback given. For the demonstration, we basically are able to upload our video here, then press the analyze writing form, then get a verdict on whether it is poor, average, or good, and then how individually the feature is performed, as well as coaching tips and the video information, including the duration, frames per second, the frames, the detected frames, and then as well as the sequences. For our model compression, after training our LSTM neural network, the challenge we faced that we had very many parameters which were manageable on the server, but too heavy for our model devices. So we applied two techniques, one being the knowledge distillation, which is basically where we train a student model using the teacher model, in this case, the LSTM neural model. So our attentional student model, which was unlike the LSTM, just processes all the frames in the video clip sequentially, whereas the attention model processes all the models simultaneously. So the model lets our frames communicate directly with each other, which is important for cyclist analysis, where patterns like pedaling rhythm and balance unfold across the clip. So this is our architecture. In layer one, basically, each frame from 7 features is projected onto 32 dimensions, and then the layer lets the frames talk to each other, leading to different types of relationships. After attention, we then add the original input back to the attention output, and the layer normalization stabilizes the values. We then process each frame independently to refine the mixed representations into useful features for classification. Our original input is then added back to attention output, and after every frame has been enriched with data from other frames, that layer then collapses into a single summary, giving us good, average, or poor. We are able to get an accuracy of 98.33%. So this significantly reduced our parameters as well as maintained our accuracy. For the pruning method, basically remove redundant low magnitude weights to create a sparse model. And for this case, a prediction accuracy of greater than 95% against the original model was required before the compressed version could be considered safe to deploy. We had 3 methods, and the first method was the one-shot 50%, where half of all the weights was zeroed in a single pass. And then it was very fast to run, produced 81.6%, a smaller file, but then there was no chance that the LSTM could adopt, since many of its weights still needed still needed to be were removed at once, which dropped the prediction argument to 49%. Method B, 70% of our weights were removed in one pass, giving the smallest file about 87.3% reduction, but the model lost even more signal, bringing the argument to 24%, which was only useful if file size was the priority and accuracy was acceptable. Method C, which was our best method, instead of putting everything at once, we're basically removing weights in 5 rounds and retraining between each round so that the model can recover. The argument stayed at 95%, but the file shrunk by only 7.9%, which was relatively low, as been demonstrated in the table below. And because of this, we chose the knowledge distillation technique since it was able to reduce the size as well as maintain the accuracy. This is how we deployed. We were able to still upload and add a video here, analyze, then get a verdict, as well as individual scores of the features we have, as well as coaching tips. For conclusion, the system successfully differentiates between skilled and unskilled riders based off the 7 biomechanical features and balance posture as well as upper body stability for the ones that greatly affect the rider's movement. For our limitations, dataset constraints, especially in relation to the domain, which is Uganda, which was a very big challenge, as well as the failure to process some of the harder samples which were unclear by the media pipe, and also our results may vary from expert cyclist analysis. In conclusion, we would like to express our sincere gratitude to Mr. Galiwango, our supervisor, for his guidance as well as his timely support whenever we needed it. Thank you so much.